Okay, so now we're going to say a little bit about efficient implementation of the reduction algorithm. Okay. And of course, one of the issues is that when you do the reduction algorithm, you're working on the combined boundary matrix, which it's like has a number of rows and columns, which is equal to the number of simplices in the complex, and so of course that in general is going to be extremely large. Okay, for practical applications with a large amount of data. Okay. But one observation, of course, is that for the most part, this boundary matrix which you construct is extremely sparse. Okay, so some observations, right? So for practical applications, right? So there are a large number of data points. So the resulting boundary matrix is very large, right? But in general, the boundary matrix is sparse. So, and basically what happens is that when you're trying to do any kind of matrix reduction on a matrix which is very sparse, then having a representation as an array or some sort of, it's like representation where you basically record the entry of every single it's like in the matrix is extremely inefficient. Okay. So basically, using some sort of array, sort of two-dimensional array, to represent the data is very inefficient. So what one often does, it's like in that situation, is to use instead something like a linked list. Okay, so instead, right, we have a linked list containing sort of only the non-zero entries of the matrix. Okay, so in the context of the reduction algorithm which we have, right, if you recall, all the operations which we did, it's like involved basically adding one column to the other. So in that situation, it's very natural then to have a linked list which just consists of the ones that's like in a given column. Okay, so for the purposes of our matrix reduction algorithm, right, which involves sort of column operations, is natural to consider a linked list for each column, right, consisting of the non-zero entries. Okay. The other thing, of course, it's like in our matrix reduction algorithm is that there's this distinguished role which the lowest one plays. Okay, and so given the fact that you want to be able to access that information very efficiently, it makes sense to have that lowest one, in some sense, to be at the top of the linked list as opposed to be at the bottom of the linked list. And so that basically suggests that in addition to having a linked list, which, it's like enumerates the ones that's like in each column in some sort of ordering, right? You want that ordering, it's like to be such that the lowest one is actually the first entry. Okay, so because of the role that the lowest one plays, right, I want the linked list to be ordered in reverse order, right? Okay, so these are just some initial observations it's like one might have, and in some sense sort of the line of reasoning it's like which informs this sort of more efficient representation. Okay, so let me now say this a little bit more formally. Okay, so we're going to do this sparse matrix representation. Okay, so as before, right, I'm going to assume that we have a monotone function f, okay, on the simplicial complex. Okay, so it's just a scalar valued function. It's like a complex with the property that the sublevel sets it's like of that function are always subcomplexes in some sense, right? And there's a nesting property. Okay, so we store the data. Okay, so given this monotone function, it's like, and the complex structure, it's like, you know that there is a compatible ordering. Of the simplices. Let's say sigma 1 to sigma m. Okay. All right. So, so as we said before, what the structure of the matrix reduction algorithm suggests is that you should have linked lists associated with every column of the matrix, and then each of those linked lists corresponds, will give you an ordered list of ones in that given column. Okay. So you can store, it's like the pointer, it's like to the first entry of each linked list, it's like in some sort of linear array. Okay, so we store the data using a linear array. Okay, let's call that the boundary. Then there are entries for each of the m simplices, right? There's a column associated with each of the m simplices, and then associated with each of these entries is a linked list, right? Okay, all right. So this is again consistent with what we've seen so far, what we discussed so far. So as I sort of alluded to, the list in the sort of boundary J, right, corresponds to the jth column of the boundary matrix. And if you recall what this actually represents, right, this really is storing the codimension 1 faces of that simplex. Okay. All right. And that observation obviously is consistent with the idea that it just stores the sort of non-zero entries, it's like of the boundary matrix, because the non-zero entries of the boundary matrix sort of column-wise, all right, are exactly the list of simplices, it's like which are codimension 1 faces of the J simplex. Okay. All right. So so all this is sort of consistent with what we've seen so far. And then, as you might expect, at the end of the algorithm, so at the end of the algorithm, right, the list in the jth column, well, the jth array entry, which corresponds to the jth column of the reduced matrix, right? Okay, sort of corresponds to the column of the reduced matrix, whose lowest one is in the jth column and jth row. Okay, all right. All right. So so this is where it's like, if you will, it's like the interpretation sort of deviates slightly, right? Normally you would expect it to be basically just the jth column, it's like of the reduced matrix, but you're sort of doing some sort of dual representation where the list in the jth entry then is going to be the one where the lowest one is in the jth row. Sorry, the list of the column that's like of the reduced matrix whose lowest one is in the jth row. Okay, so and then if there's no such column, right, the list is empty. Okay, and then all the lists are sorted in order of decreasing index, right? So again, the motivation for doing this is that that means that the lowest one is at the very top, it's like of the list. Okay. Okay. All right. Okay. So, so let's sort of just draw a picture of this. So you have this matrix, this linear array R, right? And you have a bunch of blocks. Okay, so 1 all the way up to M. Right, and say this is the jth entry. Then there's going to be a list of things. All right. And what's going to happen is that you can think of these as being sort of pointers to the sort of the simplices, if you will, right? Which are, again, which at least when you started off with, were the codimension 1 sort of faces, it's like of the jth simplex. Okay, all right. So again, it's like you have a linear array. It's like from 1 to m, with entries from 1 to m. It's like, and then for each of the entries, there's a linked list which has to do with which contains a bunch of codimension 1 simplices. Okay. All right. So now we're ready to describe the algorithm. So to describe the algorithm, that transforms sort of the boundary array, right, to R. Right, we write L for the linked list. Of the jth array entry, and we let I be the top index of this jth array entry. And again, it's like, if you remember, we've ordered the it's like the entries, it's like in the linked list, so that the one of the highest index appears first, right? So again, at least with the boundary case, it's like this just corresponds to the lowest one, if you will. So so in our original algorithm, it's like where we're sort of directly manipulating the matrix as a two-dimensional array of numbers, right? The lowest one played an important role, it's like in this. And the analogous thing, it's like in our algorithm, is this top entry. Okay. So, and then of course we say that the ith entry, the sort of ith array entry is occupied if there's a non-empty list there, and then otherwise it's unoccupied. Okay, so now we're ready to describe the algorithm. So, we're going to, it's like encode, it's like the transform version, it's like of the, the sparse representation of the boundary matrix, it's like in this array R. So I'm just going to first make a copy of the boundary matrix and put it into R, and then we're going to operate on R. Okay, and as before, we're going to cycle, it's like from essentially columns 1 to M, right? So for J equals to 1 to M, you do. And then L, okay, which is again the, okay, so I'm going to store in L, it's like the linked list associated with the jth array entry, right? So this is going to be the boundary of J dot cycle. And then I'm going to first let the R jth entry cycle be the null. So it's going to start with unoccupied, sort of a linked list with no entries in it, basically. And all right. So while L is not the null list, right? I'm going to do the following. And Rj with I equals to, sorry, Ri, which is where I is the top entry of L, is occupied. Do the following, that you let L be L plus Ri dot cycle. Okay. So again, this is sort of analogous to what we had in the previous algorithm, right? So what you can see, it's like in this construction, is that because of the way I mean, in some sense, if you recall, it's like the boundary matrix was upper triangular, right? So that means that all the entries here have index less than equal to the jth index, all right? So, so in particular, I, which is the top of L, right, is less than equal to J. So what this is basically doing is that you're trying to look for some, it's like column, it's like, well, I mean, it's like of R, right, where the lowest one is, where it has this lowest one issue, basically. Okay, and then you do essentially a column-like operation. It's like where you sort of add, it's like this cycle, if you will. Okay, so the cycle is just corresponds to the linked list, I should say. Okay. Okay, and then you end while, and then if L is not the null after this, then Ri dot cycle equals to L, and you do the end if. Okay, so it's like, so the difference, if you will, it's like in the algorithm. So this part here is still very, very similar to what you saw before. The difference in the algorithm is here, where if it's L is not the null, it's like list, then you sort of record, Ri, it's like the list Ri here with L. Okay, so this is what changes the interpretation of the thing you get. It's like at the end of the day, if we recall, it's like the entries, it's like corresponding to a situation where there's, so let me sort of take, okay, so if you recall, there's a slight difference. It's like in the interpretation of what you end up getting. It's like with R, right? In this sparse representation, normally you would expect it to be that the entries of R are really nothing more than encoding the columns. It's like of the reduced matrix R in our previous algorithm. But in this, it's like we had this slightly different interpretation where the after the transformation, it's like the list in the jth column corresponds to the columns of the reduced matrix whose lowest one is in the jth row. Okay, so this last if statement here is allowing you to do that, right? So that thing here, it doesn't have an analog. It's like in the algorithm we discussed before, and that's what changes the interpretation of what you end up storing in the sparse matrix representation. Okay. All right. And then, okay, so there's an N4 at the end of this. Okay, so that's the algorithm for the reduced, sort of the sparse representation of this reduced algorithm. So, all right, so here it's like there's an operation where you sort of add two linked lists, basically. And, you know, it's like because of the fact that the linked lists are already sorted, right, this is, you know, a relatively straightforward thing to do. Okay, so they're sort of, so in the algorithm, right, we have to add sort of two linked lists. And then this is sort of can be implemented by basically just scanning through both columns. Okay, so let me sort of maybe try to illustrate this. So let's say we have, let's call that A and B maybe. Okay, A and B, and we have a linked list which says maybe this is 1 and this is 3. Okay, maybe I'll do it in the reverse order to be consistent with the algorithm. Say 3 and 1, right? And this one is say 4 and 2, and then 1, for example. Okay. So what you do basically is that you first, so you just have pointers. It's like which point to the first entry of each list, all right? And you compare the two, right? So 4 is larger than 3, so the answer you get, which is A plus B, right, should take 4 first. Okay, so I will take 4, and then that is gone. The pointer goes to 2. I compare 3 and 2. 3 is bigger, so I put 3 in this list. I get rid of that. I increment the pointer down. Now I compare 1 and 2. 2 is bigger, so I do a 2 here. Cancels, and then this is, then now I have a 1 and 1. Okay, so when you have a 1 and 1, right, if you have modulo to arithmetic, right, then you know, the 1 1, it's like becomes a 0. Okay, so if there's if there are the same entries, it's like in both lists, and you're doing modulo to arithmetic, instead of inserting it into the list, you just ignore it. So you cancel out both, and then you sort of go to the end, and then it's like you find that you're at the end of both of the lists, so you just stop, right? So the point is that if you have A and B, where A consists of something with ones, it's like in the first row and the third row, and then B consists of something with ones in the first, second, and fourth row. When you add them together, you'll get a column, right, with ones in the second, third, and fourth rows. Okay, and then the ones, because they the ones in the first row, right, because you have 2 of them, become a 0. So this is sort of just a, you know, worked example for how you would then sort of very efficiently do the addition of 2 linked lists, which shows up in exactly this step here, right? So here you have an addition of two linked lists. And again, it's like, mindful of the fact that you have modulo 2 arithmetic. If you have an entry which shows up in both of the linked lists, you just, discard both of them, go to the next entry, and you don't add it to the linked list. It's like for the answer. Okay. Yep. So again, there's this sort of parallel scan structure. Okay. All right. So hopefully that gives you an idea of how you go about implementing these things. So maybe let me just sort of finish up this discussion. So adding these two linked lists, merging, by sort of merging them while deleting sort of both copies of every duplicated simplex. Okay, and then this is because we're doing modulo 2 arithmetic. Okay, and then as you see, it's like each addition sort of involves sort of this parallel scanning. It's like of the two sort of original linked lists, right? So let me just stop here for now. It's like, and then I'll say a little bit about how to interpret again this algorithm in a little bit. Okay, so I'll stop here for now.